Hello. Welcome to session 610, Building a Game with scenekit. Scenekit is an amazing technology that makes it easy to write casual 3D games. Because scenekit is a high-level API that integrates well with other Coco frameworks, it's really easy to write games. We built this demo for WDC, and I only required a few lines of code. We believe that building a casual 3D game with scenekit is really easy, and anybody can do that. It's really fantastic. So this is a hands-on session, so hopefully you are already familiar with the basics of scenekit. You should know that you should know what a scene graph is, that node have attributes such as geometry, camera, and light. And if not, we have great sessions about this, one just before and one last year. I encourage you to check these presentations because they have 3D slides entirely made with scenekit. So in this session, we will start really quick by showing you how to start in Xcode, how to add 3D assets to your project, and have your first scene rendered to the screen. Then we will show you our bananas demos. It's a great demo because it shows many features of the scenekit framework, and we will use that demo throughout the rest of the session. We will explain you how we made it so you can create your own games. And finally, Thomas will join me on stage to talk about performance and creating custom tools for scenekit. Okay, let's get started. The first thing you want to have when building a 3D app is a scene, is a view to render your scene. And that's just easy as you think. We are integrated into interface builder, so all what you have to do is drag an SN view from the object library and drop it onto your OS view. Then you open the inspector when you can set the view properties, and you simply specify the name of the 3D scene. You click build and run, and boom, without having to write any single line of code, you have your first scene rendered on the screen. Now, if you are starting a new project, you might want to start with the new game template. It's really convenient because it creates a universal app that runs on iPhone and iPad, and it has a full screen 3D view that displays a scene you can interact with. The way you add 3D assets to your game is via scenekit asset catalogs. Scenekit asset catalogs are a new feature in Xcode 6, and they allow you to organize and optimize your 3D assets. The structure of scenekit asset catalogs is preserved when they are copied into your target. Also, they automatically track files that are added to them or removed from them on disk. They are really convenient because they can optimize your 3D assets for you. For instance, they help with up-axis conversion. Scenekit follows the up-axis conversion, which means that the positive y-axis is the one that looks up. This is a convention that is followed by many other applications and frameworks, but some exporters do things differently and use the z-up-axis convention. With scenekit asset catalogs, you don't have to think about that. We automatically and transparently convert all the animations and geometries in your scene so that they follow the up-axis convention. We are also able to automatically interleave your geometries at build time. This means that your vertices, position, normal, and texture coordinates are stored in a single buffer that makes the GPU really happy and faster at rendering your geometries. And finally, on iOS, we support pVertice textures. If you have two versions of the same texture, one with the pVertice file extension, which is a compressed file format that is optimized for iOS, and another version, for instance, PNG, Xcode will automatically select the pVertice texture when you target iOS and the regular version when you target OS X. So this is how it works. Your artist works in their favorite authoring tool. They export all the animation and models you want to use in your app in a Collada document. Then you take over and you import this document in scenekit asset catalogs. But there is much more you can do with Xcode. To help you have a better understanding of your scene, we built a scene editor into Xcode. This tool is really great not only to allow you to have a better understanding of what is inside your scene, but it's also useful to tweak and refine the scene. For instance, with direct manipulation, you can place the nodes where you want, you can rotate them and scale them, and that's much less code to write in your app. You can also see how nodes are arranged. You can reparent them, you can merge them, you can create and delete nodes as well as node attributes. You can immediately see which node has a camera, light, or geometry attached to it. And it also allows you to have a quick look at all the entities in your scene. Remember that in scenekit, node attributes are shared by default. And this is a great way to know how many unique objects you have in your scene, and it helps for performance. Of course, we have inspectors in this editor. You can edit node properties, and as you make changes, they are automatically reflected in the viewport. This works for node attributes as well. You can edit all the camera, lights, and geometry properties that are exposed in our APIs. And finally, it works for materials. This is really cool. It allows you to finally tweak the rendering of your objects. You can control exactly how they will render in your scene, because what you see here in the editor matches exactly how scenekit will render the scene in your app. It's a huge time saver. In addition to the scene editor, we have a particle system editor. It's really useful to edit particle system properties, and it becomes very convenient when you have to do things that would be very tiresome in code. For instance, finding the right animation curve to control the size of your particles, they can take a very long time in code. With the editor and immediate feedback, it's really quick and easy. So, we already covered a lot here. You know how to work with an artist. You know how to tweak scenes in the editor. You can automatically optimize them using the asset catalogs, and you can render them on the screen without having to write any line of code. And now to show you how truly simple it is to write a casual 3D game, we built a demo. So first, it's a sample code. So might you have any question about what you are going to see on the screen, you will be able to dive into the code and see how it was done. And it's a great sample code because it illustrates many features of scenekit: animation, lighting and shadows, physics, particles, and advanced rendering. So let's have a look at the demo. So this is our game named Bananas. As you can see, we are in the jungle controlling an explorer. We use gestures to make the character walk along the path. On the track, we can collect bananas, but there are enemies. We have some animated monkeys that throw coconuts at us. To avoid coconuts, we can jump and run. Look how the scene looks gorgeous. We have per pixel real-time lighting as well as real-time shadows. Look how the character is lit when it approaches the torches. As we advance in the game, we encounter obstacles. Here is a lava flow, and falling into it is not a good idea. So here we have to start again, and you will notice how the explorer produces dust as she runs. If you look at the background, you will notice a volcano. This volcano is erupting, and this is where the lava comes from. In fact, everything that's in this scene is animated. The character and the enemies, the lava, the torches, but vines as well. And as you can see, everything is 3D in this scene. When the character moves, the camera follows in 3D space and offers new points of view. We also have a soundtrack and sound effects. There's also a basic UI that shows you how much time is left and your current score. This runs really smoothly on an iPad, but it works on iPhone 2 at 60 frames per second. Okay, thanks, Thomas.
Thank you.
So this was Bananas. It's an all Objective-C project, and it's a small project. Only 2,700 lines of code for everything you saw on screen today for iOS and OS X. And so you don't have to have a big team to write a 3D casual game with scenekit. Bananas was written by a team of one designer and only one engineer. It's really easy to make such games. So first, a quick look behind the scenes. Here is our world. It's a simple track on which the character walks. Look how palm trees and rocks do not always stand on the ground. This is because your scene should only be made of elements that will, at some point, be visible from the camera. Here is a side view. As you can see, vines aren't attached to anything, they float in the air, and the world suddenly ends. There's no need to have extra geometry pushed to the GPU if it's never rendered onto the screen. We have low polygon meshes for the mountains and the volcano in the background. It's absolutely fine to cheat when you write 3D games. Here the scene is sparse, and you have to find tricks to make the scene gorgeous but really cheap to render. So to give you some idea of reasonable numbers, here are statistics from the game. We have 10 lights in the world, but each object is only affected by 3 lights at most. We have 200K polygons in the world, but at each frame, only 80 are rendered. And to finish, we have at most 50 draw calls per frame, and that will make more sense when Thomas talks about performance. So, of course, we use scenekit asset catalogs in Bananas. We have about 25 3D documents that store animation, models, textures, and particle systems. And how do you use that many different documents in one single scene in your game? Well, let's take this example. Here we have a document which stores the jungle and another document which stores our animated monkey. And we want to use that monkey in our world. The first step is really easy. All you have to do is to load the two scenes. Where you have to be careful is that you cannot directly add the root node of one scene to another scene. This is because root nodes are not meant to be reparented. What you have to do instead is to retrieve the node you're interested in by using its name, and then add it to the original scene. And of course, you can add multiple copies of that node. So, scenekit is a high-level API that integrates very well with other APIs on our platform. So we support game controllers to control the character, but we also leverage gesture recognizers and implemented our own D-pad gesture recognizer to make the character jump and go left and right. And then on OS X, we also support game controllers and simply listen to keyboard events. So how do we move the character? First, we have to animate it. Our character is skinned, which means that it has a skeleton with bones. And by animating these bones, we can deform the geometry and make the character adopt different postures. Our character can run, jump, and be idle. And we have different animations for the bones in these files. Animating the character is then just as easy as retrieving a core animation by using the SCN scene source class. It allows us to retrieve an animation with the unique identifier of the animation that you can find in Xcode. And then animating the character is just as easy as adding this animation to the character node. Okay, so now we are animating the character, but we still have to move it. There are many ways to do that, and here is the technique we used in Bananas. In our authoring tool, we placed empty nodes at different locations in the scene. We then use a cat-mulrom spline to interpolate these values. It's a smooth parametric curve that goes through each of these locations, and then moving the character is just as easy as evaluating this function at different times between 0 and 1. And for the camera, when the character goes to the right, we simply offset the camera, and at each frame, we move it by 1/25 its distance to the character. This gives us this nice delay animation that's really pleasing when you play the game. Now, in iOS 8 and OS X Yosemite, scenekit has a native support for physics. And we use collision detection at many places in the game to make the character stay on the path, to detect when we are hit by coconuts and when we collect bananas, for instance. How does that work? Well, each scene has a physics word, which has a delegate, and each time a collision occurs in the scene, the delegate is notified and can react. We can also explicitly perform ray tests, and that's what we use to compute the altitude of the character. So we cast a ray and compute the intersection between that ray and the ground to calculate the altitude of the character. Animating items is different than animating characters. For items such as the bananas, we use actions that was presented in the previous session. They are really easy to manipulate programmatically. So here is the lighting in bananas. As you can see, we have objects that aren't affected by any light. They use a constant lighting model. For all the other objects in the scene, we add an ambient light so they are not rendered all black. Next, we add a directional key light and another directional backlight to add more contrast. Finally, for torches and lava flows, we add omnidirectional lights. With this dynamic lighting, we also want shadows, and we have multiple techniques in bananas. First, static shadows. Static shadows are suitable for objects that aren't animated in the scene, such as the palm trees. Static shadows are baked into textures, which means that they are rendered offline in an authoring tool, and that's why they are generally very complex and detailed. Setting a static shadow is as simple as setting an image to the multiple property of a material. But we also have dynamic shadows for objects that move, such as the character. For dynamic shadows, we use shadow maps. These are real-time shadows and suitable for animated objects. And making a light cast shadows is as simple as setting a property. Next, of course, you can mix techniques and use dynamic and static shadows. After you make a light cast shadows, you can simply exclude nodes that are using static shadows so that they don't cast dynamic shadows. This can also be achieved by using category bit masks. You use exclusive masks on the light and nodes that don't cast shadows. So this is one example of dynamic shadows, but we have one another, which we call projected shadows. Projected shadows are real-time as well, but they are simplified and they are very suitable for low-end devices. Using projected shadows is done by using the modulated shadow mode. You set an image to the gobo property of a light, and then every object that is lit by this light has this image projected on it. So in bananas, to make the floor only receive this image, we use category bit mask. Next, particle systems. We use particle systems extensively in bananas. We use them for torches and when the character walks. Using particle system is really easy. All you have to do is load a particle system from a file and add it to a node. And because particle systems are dynamic, we can make the character emit a lot of dust when she runs and emit nothing when she stands idle. We also have some nice visual improvements in bananas. We use geometry animation for the vines, and we use texture animation for the lava and the volcano. You might have seen that smoke is emitted by the volcano, and that the lava flow is animated. This is done using shader modifiers. What we do is we have a shader modifier that continuously updates the texture coordinates of the lava and the volcano. This is really simple. Next, we have some visual post-processing. We use the SN technique, which is new this year, and that lets us achieve color effects and image deformation. We use that in Banana when we launch the game to have this nice grayscale effect. We also use sprite kit overlays. SpoilKit overlays are really nice because they are cross-platform. They work on iOS and OS X, and they let you build UIs that work everywhere. In SpoilKit, in Bananas, we use that to display a simple UI that shows you the final score, and when you're playing, it shows you the current time and your score. And finally, we use an SK action to play sound in the game. So as you saw, we have a soundtrack as well as sound effects. So I hope we showed you how simple it is to write a casual 3D games with scenekit. We truly believe that anyone, even a small team, can write games with scenekit. And with that, I hand it over to Thomas to talk about performance. Thanks.
Thank you. Okay, so let's talk about performance now. So Xcode has some great tools to get information about performance, and in particular with graphics performance with the graphics report that you probably already know. In this release of Xcode 6, we are adding a new report that we call the scenekit report that will give you CPU time information about your game. So this report is not available in the first seed of Xcode 6 yet, so you will have to wait for the next seed to have it in hand. But I would like to present how it works now, since we are talking about performance. So this report will give you timing information about all the different steps of your game loop. You remember, your game loop looks like this. It's made of both callbacks that you implement to do your game logic, and also of scenekit internal process like the rendering itself or the evaluation of physics and animations and constraints. So the scenekit reports will give you, will tell you how many milliseconds are spent into those different steps. And this is for iOS only, but on OS X we have something equivalent directly available in the SCN view with the show statistics property. If you set this property to yes, it will display a little overlay on top of your view that you can expand to get more detailed statistics. And basically, it contains the same information as the iOS report. So here it is. Okay. And so this is how to get information. Now let's see how to analyze this information. If your game is running slow, the first thing to understand is if you are limited by the CPU or by the GPU. For this, use the graphic reports and look at the third column. It will tell you how many milliseconds are spent on the CPU side and the GPU side. Both should be under 16 milliseconds if you want to run your game at 60 frames per second. Now, let's say we are limited by the GPU, let's say. You can switch to the scenekit reports to get details about the different steps. And then, depending on the numbers that are returned, there are some obvious actions you can do. For example, if it says that most of the time is spent in physics, you might want to reduce the number of dynamic bodies in your scene or simplify the shape of your bodies. And if it's in particles, you want to probably to reduce the number of emitters or reduce the number of emitted particles. So these are the obvious things. Now, less obvious, if the time is spent in the rendering itself or when pushing the OpenGL commands, then it's very likely because your scene requires too many draw calls to render. The number of draw calls is something very important for your frame rate. And if you have too many draw calls, it will impact your CPU time. You can check how many draw calls your scene is doing with the scenekit report by looking at the third column here. This is for iOS. On OS X, you have the same information in the statistics overlay in the lower right corner. And if this number is big, and if you are limited by the CPU, you want to reduce the number of draw calls. And to do that, what you can try to do is to flatten your static objects into one single node. For example, in Banana, we have many plants and palm trees that are static. And instead of having one node for every plant, we grouped them and flattened them into a single node so that it ends up into a single draw call to render many plants at the same time. To flatten objects, you have two options. You can ask your artist to flatten directly in the 3D software. 3D software have great tools to flatten everything into a single object. This is the recommended way because everything is pre-computed, so there's nothing to do at runtime, and it is obviously faster. Now, if needed, you can also flatten things programmatically with the flattened clone method on SCN node. It will flatten the entire node tree and return a new node with no child node that render exactly the same. So flattening is really great to improve the number of draw calls, but don't flatten too much, because let's say you have a very large level. If you flatten everything into a single node, you will end up into a giant mesh with millions of polygons. And so you will lose the benefit of the culling of the objects that are not visible. Your big mesh will be always visible. And so you will push millions of polygons at every frame, which is obviously not good for the performance. And also, your huge mesh will be lit by all the lights in the world, which is not good for the performance, and I will explain why after. So here is how we did in Banana. We first split the level into chunks that are about the width of the viewport. That way, when the character progresses, we can directly scenekit automatically culls the chunks that are not visible, and so they are not pushed to the rendering pipeline at all. And since almost everything in one chunk is flattened, that means that we are only rendering one or two chunks at the same time, and so we are really pushing a few number of draw calls to render the chunks that are visible. So that's if you are CPU limited. Now, if you are GPU limited, again, you can use the graphic reports and look at the third column to check how many milliseconds you are using on the GPU side. And if you are GPU limited, there are two things to look at. The first one is the tiler on one side, and the second one is the renderer or device. So this is here in the second column. So let's consider the renderer and device for now. If your renderer and device usage are at 100%, it is very likely because you are either fill rate limited or you are using too complex fragment shaders. So let's consider first the fill rate. The fill rate means, if you are fill rate limited, it means that you are asking the GPU to render more pixels, more fragments per second that it can actually render. If that happens, you can first try to play with the content scale factor of your view. By default, scenekit is using the 2x context scale factor, which means fully retina. But you can try, depending on the device, to switch to 1x or any intermediate values. You can also try to reduce the number of post-process effects, since they are usually full screen effects. They impact the fill rate. So typically deferred shadows, depth of field, reflective floors, and all your custom post-processing. Reduce that if you are fill rate limited. Last, you can also try to play with the anti-aliasing level by setting the anti-aliasing mode property of the view to one of the available constants, known to disable it, and multi-sampling for X for the multi-sampling. Note that on iOS, it's already turned off by default, and it's for X by default on OS X. So that's for the fill rate. Now, the other reason could be that you are using too complex fragment shaders. And most of the time, the complexity of your shaders directly depends on the complexity of the lighting in your scene. So I remind that there are two types of lightings, dynamic lightings and static lightings. With static lighting, all the light informations are baked into textures. So this is super fast, it can look really great, but obviously it only works with objects that are static. And so here we'll focus on dynamic lightings that we need to use when objects are moving. One thing important about lights is their area of influence. So you can configure the attenuation distance with the attenuation end distance, and beyond that distance, a light won't influence the other objects. And this part is really important because regarding the performance, what matters is not the total number of light in your scene, it's the number of lights that influence a given object. So for example, here, I have 3 lights in my scene, but I configure the attenuation distance so that most of the objects are only affected by 1 light or 2 lights in the worst case. So that means that the lights with the the objects with the 1 will be, the rendering of them will be relatively cheap. The rendering of the objects with the 2 will be slightly more expensive, but at least no objects in that scene will be affected by 3 omni lights at the same time. Here's how we did it in Banana. We placed the torches and the lava so that when the character progresses in the game, it is never affected by more than 1 torch or 1 lava at a time. Related to lighting, shadows. Shadows are also expensive. Again, there are 2 types of shadows, dynamic and static. For static, everything is baked into textures with 3D tools. And it's fast, so let's focus on dynamic shadows for dynamic objects. The first thing to consider is what mode of shadow you want to use. If you want to use the real dynamic shadows with the forward mode, which is the default. And you might want to consider projected shadows for low-end devices. With the right shadow image, it can look great too, and it is really fast. If you are using dynamic shadows, there are still a few things you can do to optimize the performance. The first thing is to play with the size of the shadow map. When you are using dynamic shadows, scenekit computes such shadow maps at every frame, typically by rendering your scene from the light point of view. So if you are fill rate limited, by setting the shadow map size to a smaller size, it will reduce the fill rate impact of the shadow map size computation. You can also play with the shadow sample count property on SCN Light. This improves a lot the complexity of the shader that is generated to compute the shadows. Note that on iOS, it is already 1x by default, which corresponds to hard shadows, and it is 8x by default on OS X for smooth shadows. Still about GPU, one more reason to be limited by the renderer is when you are doing too many texture samples in your game. So the first thing to check is to make sure that you are not using unnecessarily large textures in your game. For example, if your texture is always rendered small on screen, there is no need to have a huge texture for that. One more thing to do is it's better, if you are using tons of textures, it's better to pack them into a texture atlas. For that, 3D softwares have great tools to bake your textures into texture atlases, and you can also use scenekit to generate texture atlases for you. If you need to use very large textures, though, you can also try to play with MIP mapping. The MIP mapping improves the performance a lot when you are rendering a large texture at a small size, because it will pre-compute smaller resolution of your texture. It can also improve the rendering by reducing some aliasing effects and some moire effects. It has some drawbacks, though. It takes more time to load, and it uses also slightly more memory. To turn on the MIP mapping, just set the MIP filter property on a material SN material property. Set it to linear to turn it on and none to turn it off. Okay. So that was for the renderer and device part. Now let's say you are limited by the tiler this time. If you are limited by the tiler, that means that you are pushing too many vertices to the GPU, and so by extension that you have too many polygons. You can check how many polygons your scene is rendering at every frame with the scenekit report here. This is for iOS. On OS X, you have the equivalent in the statistics overlay here. And so if you have too many polygons, obviously the first thing you can try is to reduce the number of polygons in your models. And the second thing you can try also is to play with level of detail. scenekit has some support for level of details. For example, here, I have 3 versions of these teapots with more or less polygons, and so with a higher and lower quality. And I can group them into a single level of detail array and assign that to my geometry. Then scenekit will automatically use the right level of detail depending on how big your model is displayed on screen. So you can associate to each resolution either a distance from the camera or a screen radius and to tell scenekit what level of detail it should use. And this can help a lot to reduce the number of polygons in your game, because with this example here, for example, the teapots in the background are rendered with a low resolution, and so most of the teapots are using very low, a small number of polygons instead of having the huge resolution all the time. So to sum up all this, when your game is running slow, you first need to understand if you are limited by the CPU or GPU, and if it's with the GPU, you have to check the tiler or the renderer and device. If you're limited by the CPU, you can try to reduce the number of draw calls by flattening your scenes. And also, if you are using if your time is spent, in physics or animations, you can try to reduce that. If you are limited by the tiler, you can try to play with level of details to reduce the number of polygons, and you can also try to split your scene in smaller chunks to leverage the culling. If you are limited by the renderer or device, you can try to simplify your materials. It will end up in simpler shaders. You can simplify your lighting, try to reduce the size of your textures, and try to turn on mip mapping if you are using large textures. And if you are fill rate limited, you can also try to reduce the number of full screen post-process. Now some more other performance notes. First, about sharing. When you copy a node in scenekit, by default, it shares the attributes. So this is ideal for the performance. But now, let's say you want to modify node a.geometry.a.material. It will also modify the color of node B. And so this is a common pitfall. If it's what you want, that's perfect. Now, if you want a different material for node B, what you have to do first is to copy the geometry as well. And since the geometry is immutable, it is relatively cheap because no geometry data is actually copied. It's just shared. And then you can just simply copy the material as well. And now you can modify material A and material B independently to have a different material colors for your objects. Another note, this time about preloading. By default, scenekit will load the information on the GPU when needed. That means that when your objects are never rendered, nothing is pushed to the GPU. And the first time an object appears on screen, we compute everything the GPU needs to render that object. And depending on the complexity of this object, it can take some time, and in some cases, it can make you to miss some frame, and so suffer from frame drops. To avoid that, you can preload your objects, if you want, with the prepare objects with completion handler on SCN view. You can pass to these methods the following objects. If you pass a material instance, scenekit will pre-compute all the textures that are referenced by this material. If you pass the geometry, it will pre-compute all the geometry buffers, like the vertices, normals, and texture coordinates, and also all the materials that are referenced by this geometry. If you pass a node, it will preload the entire node tree, including all the geometries that are attached to these nodes. And last, if you pass the entire scene, it can do even more. It will preload the node tree, but also all the shaders that are needed to render the objects. It only works when you pass a scene, because scenekit needs to know how many lights you have in your scene to pre-compute the right shaders. In Banana, for example, at launch, we preload the entire scene to have almost all of our shaders directly ready when the game starts. Okay, some notes about custom tools and workflow now. So I'm already presented how to manage your assets in assets catalogs. But at some point, you may want also to customize your workflow by, for example, building your own tools that will process your assets or having your own tools to debug your game. And for this, scenekit provides some APIs to help you. The first one is archiving. Now, this is new in this release. All the objects of the scene graph, of the API, conforms to NS secure coding. So that allows you to archive whatever object and unarchive with a well-known NS keyed archiver, for example. scenekit also allows you to export your scene as Collada. And here, the advantage is that you can export to Collada and import it back to a 3D software. However, note that only a subset of scenekit can be exported to Collada. If we compare both, so the first difference is that archives can be directly loaded on iOS, whether Collada files need to go through Xcode first if you want to load them on iOS. Then you can import back Collada files in 3D software, but obviously you can't import scenekit archives. Both support the scene graph basics, like the node hierarchies, the node names, the geometries, all the materials, and the animations. They work for both. But advanced features like actions, physics, particles, and even custom shaders, everything is archived, works with archives, but they are not supported by Collada. One more note, as mentioned in the previous session, scenekit is now fully bridged with JavaScript. This can be really helpful for if you want to customize your workflow or have debug tools to debug your games. It's bridged with JavaScript core. And so the banana sample code we shown earlier is available on the developer website. We also have 3 other sample codes available. The little car demo we shown in the previous session, the demo that was shown in the State of the Union, and the 3D slide that was shown in the previous session that is for OS X only. For more information, please contact our evangelists, Alan Schaefer and Philippe Iliescu. We have a new gorgeous documentation available on the developer website as well. And we have a dedicated forum for scenekit on devforum.apple.com. Don't hesitate to ask your questions there. Some related sessions. So obviously the previous sessions about what's new in scenekit. Also have a look to the SpriteKit sessions, since both can work well together to achieve great stuff. Thank you.